And the first speaker today is Professor Alexander Kiselev from Duke University. And Professor Kiselev is going to talk about small scales and singularity formation in fluid dynamics. Go ahead.
Thank you. Does it work? Yeah, okay. Thank you. It's an honor to speak here, and thanks for the introduction. So what I will talk about is primarily Euler equation, but also some related equations. And the main question that I'm going to talk about is singularity formation and more generally formation of small scales in solutions. So let me start by introducing the equation. Euler equation actually goes back to 1755. And as far as I know, it's the second PDE ever written down, which is actually quite amazing. The first one, by D'Alembert, came just 8 years earlier. And it's a linear equation, it's not too complicated. Euler equation is already non-linear, and it's also non-local. So this is something that is maybe not completely obvious from this form, but it will be obvious just a minute later, in a minute. So I will be interested in a setting where equation is set on a domain in R2 or R3, and the boundary condition is a natural no penetration boundary condition for the fluid velocity on the boundary. So just to set a connection, let me also write Navier-Stokes equation. I won't talk much about Navier-Stokes equation, but Navier-Stokes equation just adds a Laplacian, and it's actually surprising that it took almost 100 years for people to agree what is the right term to model viscosity. So Euler equation is what's called ideal fluid, so fluid is incompressible and inviscid. Now, for Navier-Stokes equation, also boundary condition is different, which is important, but I won't talk too much about it. But in some sense, the heart is the same in both equations. It's nonlinearity. And so, apparently, in his correspondence, Euler complained of his inability to solve Euler equation explicitly for arbitrary initial data. That was the ambition of the time. I think he'd feel much better today. But later, focus switched to questions like, okay, so can at least we guarantee that solutions exist, they are unique, what sort of for reasonable initial data, or could there singularities form? And if that happens, what they mean? Right, what they mean for uniqueness, what they mean in terms of physical phenomena which may be associated with it. And the story is very different in this respect in 2 and 3 dimensions. And to see that more clearly, it is most convenient to introduce a quantity which is called vorticity, it's curl of velocity. And then in vorticity form, Euler equation looks like this. Oops. Yeah, this. Okay? And so this is Euler equation in vorticity form. To regard it as equation for vorticity, we need a way to recover velocity, and this is done by Biot-Savart law. So this KD is generally integral operator, and that's where non-locality comes in. So typically, it depends on everywhere in domain. So velocity depends on vorticity everywhere in domain. It's the same for pressure in the original form. It's just less obvious. And now this term on the right-hand side is called vortex stretching term. It influences size of vorticity. And in fact, it is absent in 2 dimensions. It's not too hard to see that. And so for that reason, 2 and 3 dimensions really are quite different. So let me now talk for a while about 2-dimensional Euler equation. So this is equation, it has a simpler form. And Biot-Savart law takes also simpler form. It's just grad perp, so rotated gradient, applied to Dirichlet-Laplacian inverse. And to analyze this equation, it's convenient to introduce trajectories. These are just trajectories of fluid particles moving with the fluid. So then vorticity in 2 dimensions is carried along the trajectory. So it does not change along the trajectory, something not hard to see just from the equation. And this map, trajectory map, it's incompressible because velocity is divergence free, and it's also can be shown to be bijective and is sufficiently regular if velocity is regular. So it can be inverted, and then the solution is just a coordinate change, a volume preserving coordinate change of the initial data. So in particular, there are lots of conserved quantities. L infinity norm is conserved, all LP norms are conserved. And so global regularity result for 2D Euler equation goes back to 1930s by Wollibner and Hölder. These are 2 different independent works. And so I stated for C1, but it's really any CN would do here the same way. So if you start with a C1 initial data, you have a global unique solution which is in C1. And moreover, there is an estimate on the growth of derivatives, on generation of small scales. A similar bound is valid for any order derivatives. And what's unusual, a little bit unusual about it, is that this is double exponential. So of course, exponential growth is quite common, and double exponential is a little bit more rare. And you can even argue that it's almost like a singularity, because e to the power 5 is more than number of particles in the universe. So it's a pretty fast growth. And so key ingredient in the proof is Kato inequality or something similar. So if you want to estimate gradients of the vorticity, you quickly realize that you have to estimate derivatives of the inverse flow map. And this is depends on derivatives of the velocity. If there is no change in the velocity, everything just moves in parallel, no gradients is being created. So it's not surprising then that what you want to estimate is L infinity of the derivatives of velocity. And these are Ritz transforms of omega, right? So velocity is one derivative more regular than vorticity. Derivatives of velocity is at the same level. So these are 0-degree homogeneous operators on Fourier side. And so you kind of naively may expect something like this, and it's true in L2, it's true in any LP between 1 and infinity, but not at the endpoints. And so actually at the endpoints you have to pay an extra price, and you have to add a log of higher order norm. And it's exactly this log that creates double exponential. So without this log, you would have an upper exponential bound on the growth of derivatives. But of course, what's not obvious is that it's kind of general estimate. It's a Fourier analytic reason for double exponential. But does it really happen in dynamics? Do configurations like that appear? And so examples with growth of derivatives in solutions of 2D Euler go back to Udovich. He got some infinite growth, not very quantitative bound. Then Nadirashvili built an example with linear growth, and his example works in an annulus, and essentially it's a shear which is stable with respect to some perturbations, and then he puts this perturbation on top of the shear and it gets stretched. So linear growth comes from shear. It's exactly what one would expect. And then one more work I'd like to mention is Bowery-Chemin, where there is no growth, but nevertheless it's important. So they constructed example of singular cross flow. So in their example, vorticity is odd in x1 and x2, so in both variables. I think of a periodic setting, and it's actually not even continuous, so it's L infinity. It's 1 minus 1, like on this picture. Now, this solution makes sense. You can define it uniquely by Udovich theory, what's called Udovich theory. So L infinity, usually it's L infinity L1, but L infinity and periodic and mean zero is also okay. So what's remarkable about this example is that velocity on the separatrix, U1, has a log Lipschitz behavior. So it's not quite Lipschitz, there's an extra log. And if you track a trajectory here on the separatrix, it will approach the origin exactly at double exponential rate. And so if you had a passive scalar advected by this flow, then A flow like that would create very, very strong growth. In particular, double exponential can happen. Now, of course, for smooth flows, it's sort of hard to see how this could work, because smooth flow would have to approach this configuration with a jump, and somehow you should be able to put something on top of it, exactly where by odd symmetry, actually the vorticity is 0. And you want odd symmetry to maintain some degree of stability and control over the scenario. So nevertheless, this idea of kind of looking for growth in a similar configuration was used by Denisov. So first I want to say that he constructed an example where gradient of vorticity grows superlinearly in time for all times, also on the torus, without boundaries. And then he also constructed an example where initial data can have double exponential bursts of growth. So if you provide a time, then he can build initial data so that there will be this very, very fast burst of growth, exactly by smoothing out Bauer-Richemont and tracking it for a while, then control is lost. So a few years ago, jointly with Vladimir Shverek, we proved the following theorem. We work on the unit disk, and we find initial data, which is C infinity. Initial gradient is bigger than 1. And then there is a lower exponential, double exponential bound in time for all times. So this shows that this upper bound, going back to Liebner and Herder, is in fact qualitatively sharp. And double exponential growth can happen for all times. Our work has been inspired by numerical experiments by Luo and Hao, who propose a new scenario for 3D Euler singularity. And I will talk about it a little later. So as in their scenario, in our example, growth happens at the boundary. And so this example has been generalized by Zhu to any domain with a symmetry axis, and Zlatosh extended and improved some of our techniques to construct examples of exponential growth on the torus without boundaries, but for second derivatives of the vorticity. So I think that symmetry is really necessary for the proof, and I'm not sure what happens if there is no symmetry in the domain, but as you'll see, the scenario is of hyperbolic point of flow at the boundary. I strongly suspect whenever you have configuration like that, then there may be very fast growth. So let me say a few words about the proof. This is probably my most technical slide. So we take initial data and omega, which is odd with respect to x1. So then we can look only at the half circle, right? So symmetry determines what happens everywhere else. And the first step is to understand and simplify the Biot-Savart law near the point where the growth will be. And the growth will be at the boundary, here at the bottom. So in fact, my origin is set here, right? Not in the center of the circle. So this is the origin. And here's the main lemma, which gives a simplified and very useful representation of the flow near that point. So first of all, one has to throw out some exceptional sector where this estimate will be valid. So this is very thin sector where estimate for U1 is not valid. We have to discard it. Gamma is something that we can fix from the very beginning. And then if we look close enough to the origin, then U1 has this kind of representation. So this term here, we can think of it as a main term, and this is an error term. So this is Lipschitz error term. The constant B1 is bounded just by the size of initial data and some constant which depends only on gamma. So the main term is constructed in a way that as omega approaches the origin, right? So points where omega has some fixed value more than 0. As they approach the origin, remember that omega is odd, so it's 0 here. But if these values approach the origin, then this term here, this integral, is logarithmic. Logarithmic in distance to those points where omega has some larger than 0 larger than fixed constant value. So that's exactly how this singularity works. So one can think of this term as a sort of a smooth analog and more quantitative analog of Bauer-Rieschema, right? So you do see how this log may appear if you can only control what the vorticity does. And there's a very similar formula for U2. You have to throw away a sector near the other axis. I didn't put it on the picture. But the coefficient in front of the x2 term here is exactly the same as for u1. So in fact, if you discard the error terms, then the flow is exactly hyperbolic. Okay, so it's just trajectories are pure hyperboles. Now the integral here is over what I like to call a look-back set. It's just y1 bigger or equal than x1, and y2 is bigger or equal than x2. So, of course, Biot-Savart law integrates over everywhere, and the parts away from Q as well. But this turned out to be possible to put that into errors. There's just one more remark I want to make about these formulas, is that there is a sort of a hidden comparison principle in them, which is actually crucial for proof of double exponential. And this comparison principle is roughly that if your point is closer to the origin, then the region of integration is larger. And it's not strict. You can have a point really close, but then since there are two dimensions, you can have another point which is further away, but it's closer in one of the dimensions. But it turns out that up to Lipschitz errors, there is this such comparison principle. And so here's a quick application of this main lemma, and it's an informal corollary that exponential growth is easy to show. And so for exponential growth, let's take vorticity, which is 1 on the right semicircle, for x1 bigger than some small delta, like a delta from lemma, for example, so that for points closer than delta to the origin, we have this representation. And then it's odd, so it transitions from 1 to -1. Then since the dynamics is volume preserving, is incompressible, we know that the measure of points of a solution where vorticity is less than 1 is always the same. It's less than equal than delta, right? So the width of the strip, or 2 delta, of the order of delta. And so this is this factor that appeared in the formula for the velocity, and we can imagine what happens what is the smallest it can be. Even if vorticity conspires so that all the small values end up exactly where the kernel is largest, which would be near origin in some sector, still they can only fill out a sector of radius square root of delta, right? That's because their measure is always small. And then to compute the size of this factor, you are integrating from square root of delta to some constant, so you get log delta -1 order. And if delta is small enough, you can choose it small enough so that it will beat these errors for all times. And then looking at a trajectory which goes along the boundary, right? It stays on the boundary due to the boundary condition. You see that it's always pushing towards the origin, and it's always pushing it like with some constant, in fact, with a large constant if you want to. And so this will create exponential growth in the gradient of solution, since vorticity will move with this trajectory and create create growth. So to get double exponential, one has to work harder and control a region of fluid to get actually not just that this factor is large, but it's growing. And it's sort of a quintessentially non-linear argument. So you cannot, you cannot use this common idea, which is actually behind Derashvili or Denis, for example, that you have some background stable flow which will create your small scales. So here, this way you can only get exponential. Here you have to improve to see how the flow actually affects, and you have to capture non-linear feedback loop. So U will carry omega closer to the origin, and omega will enhance the velocity. And to control this non-trivial region of high values of vorticity approaching the origin, you really need this comparison principle. that I mentioned. Okay, so now let me talk about 3D Euler equations. So this is a 2D Euler part. So now there is vortex stretching term coming back. So what is known in 3D, and obviously I cannot do a comprehensive review, so I'll just touch upon some basic results. So first of all, there is local well-posedness in appropriate spaces like sufficiently high order Sobolev spaces. There is a number of conditional regularity criteria, like Bill-Kato-Maida is one of the better known ones. So what needs to happen in order for blow-up to happen? There is a little bit different flavor of result, Konstantin, Pfefferman, Maida, with later refinements by Tom Howe and collaborators. And this is more geometric in flavor, so it says that if direction of vorticity varies regularly, then again blow-up cannot happen. And then there's been a large number of numerical simulations seeking to capture a singular scenario. And again, this is far from a complete list, and if there are people in the room who did one too, and I didn't put it on the slide, I apologize. But you know, it's really a lot. It's probably not even half of all that's been done. I think it's fair to say that overall conclusion of these simulations is inconclusive. There have been simulations that produced scenario and then more careful ruled out singularity formation, or even analytical work ruled out singularity formation. So for example, Konstantin Pfefferman-Maida work has been stimulated by one such numerical experiment. But let me now focus on one of the most recent simulations, which looks actually quite promising. And this is a Luo-Howe simulation. So they look at axisymmetric flow in a cylinder. So cylinder has real boundary. The setting is periodic in Z. It's also odd in Z. Now, since flow is axisymmetric, 3D Euler can be written in terms of just angular vorticity and angular velocity swirl. And so this is this kind of simplified system for axisymmetric 3D Euler. And there is a Biot-Savart law which looks a little bit nastier than 2D. So effectively the system is 2D. There's just R and Z variables. But in fact it's not too far from the 2D Biot-Savart law, especially at the boundary where R is 1. So the main difference is various factors of R in the system. And so what they start from, Luo and Howe, is just swirl. Vorticity, angular vorticity is originally 0. So it's swirl going like that. And then this spontaneously generates angular vorticity. So this manifests itself in toroidal rolls. So toroidal rolls form. And this is a cut by fixed theta of the picture. And very fast growth is observed at this point, at a ring of hyperbolic points on the boundary. You can see from the equation how this vorticity is generated. These flows are called secondary flows, actually a well-known phenomenon. It turns out that there is a relatively little paper by Einstein on the effects of secondary flow for rivers. So Einstein did fluid mechanics too. So I want to mention one more paper while I'm talking about Luo's scenario, which is in a completely different, quite a bit different style, but it's relevant here. So it's paper by So et al. It's physics paper, it's experimental paper. There are 8 authors. The last author is de Broglie. That's often the ideology, right? So they look at a very similar geometry. It's a cylinder, but it's an experiment. So there are real propellers driving fluid, and there is turbulent flow. And then they have a camera and small particles in the fluid, and they capture how the velocity field looks like in a planar region near the axis of the fluid. And then what they're interested in is what they call instances of extreme dissipation. So it has, of course, direct connection to turbulence and analysis of turbulence. So they have a way of estimating these extreme dissipation events. And what they then do is they also provide snapshots of how fluid velocity looks during one of these exceptional events. So these are very rare events. And in fact, in 75% of these rare exceptional high dissipation events, what they see is what they call front hyperbolic points, front hyperbolic points. So these are two masses of fluid which are colliding, and then there's usually a hyperbolic point involved. So this scenario of hyperbolic point is quite interesting. And then the rest of 25, they also have other pictures, jets, spirals, and cusps. So if you try to analyze Hao-Law's scenario, before I go there, so there is a different representation of Hao-Law's scenario, which I like because it looks a little bit simpler, but it's morally the same. And it's 2D Boussinesq system. So in 2D Boussinesq system, that's ideal fluid in gravity field. And you see that the structure of the system is very similar to 3D Euler. So omega is just omega phi over r. Ru phi is essentially density or temperature for the Boussinesq. And Biot-Savart law becomes just usual 2D Biot-Savart law. And away from the axis, that should be pretty similar to 3D axisymmetric Euler. And so the picture is essentially just the picture for the 3D Euler, but put on the side, right, rotated by pi over 2. So there is a warmer fluid going up, and so there are rolls like this that Boussinesq creates. So the global regularity for this system, of course, is also known. It's actually on the list of 11 great problems of mathematical hydrodynamics by Udovic. And if theta is constant, then you just arrive at Euler equation. And essentially, that was exactly the motivation for us and for Vladimir Shverek and myself, is to start understanding Hao-Law's scenario by first looking what happens into the Euler in a similar geometry. Right, and that's exactly the geometry that we have in that example, and it was interesting for 2D Euler as well. So if you try to analyze Hao-Law's scenario and you try to extend 2D Euler analysis to it, the difficulties are basically that vorticity now needs to grow, and remember this very nice representation of fluid velocity near origin. Well, it's hard to establish it now because if you do like heuristic computations of what you get from numerics and try to see, in fact, these error terms that used to be error, right? There was main term with this extra logarithm. Now error terms seem to be of the same order actually. So it's quite a bit more delicate. And another issue is that vorticity is no longer sign definite because you have this forcing by the derivative. So what has been done so far, the two models of Hao-Law's scenario have been, well, more than two models, but let me first talk about two 1D models of Hao-Law's scenario. So you can think of these models as set on the boundary. So we are just looking at what happens here. And then, of course, we need a closure. We need to close Biot-Savart law to kind of recover U from vorticity just on the boundary. And so there are two models, Hao-Law model, where Ux is Hilbert transform of omega. And that's actually can be derived from the real 2D Biot-Savart law if you assume boundary layer structure of vorticity. So if you assume that vorticity is in a boundary layer near the boundary, and in that layer it's independent of x2, then you get exactly this law. Of course, scale dimensionally also correct. U is one derivative better than omega. And there are further terms in this law where the width of the boundary layer enters, but they are more regular, and in fact, one can show that they don't matter. You can add them, you get same results. And then the second model is CKY model, and here the Biot-Savart law is more explicit, and it's clearly inspired by the main lemma, right? So it's same representation for velocity, kind of a one-dimensional analog of that representation of velocity. And so for these two models, you have local well-posedness, and you also have finite time blow-up. So one can prove finite time blow-up for these models. And basically, let's think about CKY model because it's so explicit. It's, by the way, if you write out this Biot-Savart law and integrate, you realize it's not too different from CKY law. It's a little bit more complex, but it's not too different. And so in these models, one can really see and track the nonlinear feedback loop which creates the singularity and which leads to singularity formation. So you start with theta non-zero, and vorticity is originally 0. And then derivative of theta will create vorticity here, but it's far from the origin. The kernel is very nice away from the origin, so it doesn't have much influence. But then also vorticity will be created here by this sharper gradient. And then as this vorticity is created, it generates velocity, and velocity pushes theta more towards the origin, and there's this nonlinear feedback loop which switches on. So as the gradient becomes sharper, also vorticity becomes stronger. And so if you track this, and it's most convenient to do it with trajectories, so if you look at trajectories and you take psi, which is log of the inverse of trajectory, then morally, and I'm oversimplifying here, but this is a kind of differential inequality that you get for psi, and that's of course very blow-uppy inequality. So there's been other work along these lines, other models, 1D models with a bit more complex Biot-Savart law, and 2D models with, but these models still look at simplified Biot-Savart laws and sometimes simplified forcing terms. So I'd like to mention some other work which has also been other recent work and in a different direction and looking at different scenarios. So Terry Tao looked at what I would call Fourier side-inspired models. So essentially the inspiration from his construction goes back, I think, to shell models, in particular to Katz-Pavlovich model, where you basically take dyadic shells and you integrate energy over these shells, and then you get you take a coupled system of ODEs which model propagation of energy on Fourier side. And so Terry builds more complex models for Navier-Stokes and Euler. They still conserve energy, but not all, of course, features of Euler and Navier-Stokes. And his philosophy is a sort of self-similar cascade of energy to higher modes. So he calls it perfect fluid Turing machine, that fluid configuration of fluid reassembles in the same configuration on a smaller scale, more intense, and it repeats over a geometric series of times. And the scaling is such that this leads to finite time blow-up. And Brenner, Hormoz, and Pumir suggested a particular implementation of this idea. It's a physics paper, so it's heuristics, but it's based on vortex filaments which flatten into vortex sheet, and then through Kelvin-Helmholtz instability, these sheets break up into smaller vortex filaments, and this happens iteratively. So one more work I'd like to mention is work by Elgindi and Jeong, and their work is for both Boussinesq and also 3D Euler, symmetric 3D Euler. And so their scenario is basically very similar to Hoare law, but now instead of just having a half plane where Hoare law is set, their example is set at an angle. So you take an angle like this, and the vorticity is still odd with respect to x1 variable. And the kind of data they look at, it's a vorticity which is zero homogeneous in radial variables, so independent of radial variables. So the initial data is already just L infinity, because at the origin you don't have continuity. And so they prove local well-posedness in a specially constructed space for these kinds of solutions. And of course, since there's no dependence of radius and vorticity, you can get an effective one-dimensional equation, just an angular variable, and they show blow-up in that equation. So these solutions are infinite energy, But what they managed to do is to cut off these solutions, to make them finite energy. So of course, there were earlier examples of blow-up in 3D Euler for infinite energy by Childress, even for 2D, and by Konstantin and others. But they managed to make their solutions finite energy. So this is quite interesting. The corner exactly plays a role in this cutoff procedure. So and in 1D system as well. So they really need this corner. So nevertheless, I think that there is kind of evidence that Howlow's scenario is quite promising. So far, all models and construction by Al-Gindi and Jong suggest that finite time blow-up is indeed likely. So there is a scenario, and it hasn't been ruled out so far. So now I'd like to talk about one more direction, which is, so now we are moving on from Euler, and I'd like to talk about the SQG equation a little bit. And what I'll talk about is connected, at least on a technical level, to Euler. But of course, SQG is also a close relative of Euler. And here's the SQG equation. In fact, SQG is value 1/2 here. So it's exactly like 2D Euler. The form is like 2D Euler. But the Biot-Savart law is more singular. So for SQG, you have one derivative more singular. And then the whole range of alpha is called modified SQG range. So in fact, if this equation didn't exist, it would be worth inventing it. Because it's a very natural question. Like Euler, we barely closed, right? It barely closes. We get this double exponential upper bound. We barely get global regularity. So what happens if we just push a little bit off? But in fact, SQG it comes from geophysical science, atmospheric science. It can be derived from 3D Navier-Stokes coupled with temperature equation through gravity and rotating 3D Navier-Stokes on, let's say, in a half plane. So under a number of assumptions, one gets SQG equation as an equation for temperature on the boundary, on the surface of the planet. And so in mathematical literature, it first appeared in '94 in work Konstantin Maida and Tabak, and then Cordoba and Cordoba-Pfefferman did some interesting work on ruling out a singular scenario which was proposed in Konstantin Maida-Tabak, the closing front. So in fact, it's not known if these equations are globally regular or can have finite time blow-up for smooth initial data as soon as alpha is greater than 0. So it's an open question. Okay. And so I will look at not at smooth initial data, but at a little bit different class of initial data, which are called patches. And these are fairly classical. And vorticity is just a sum of characteristic functions of disjoint domains, and boundaries of domains are sufficiently regular. And then in this context, the question of regularity and global regularity refers to preservation of the class of regularity of the boundary and lack of collisions or self-intersections by patches. But first one, of course, has to justify existence of solutions at this level, right? These are not very regular. And in 2D Euler case, this follows from Udovich theory, that these solutions exist and are unique, exist globally. So global well-posedness in the situation without boundary was shown by Chemin with later proofs by Bertozzi, Konstantin, and Serfati. And I'm skipping some pretty dramatic story here because first numerical simulations actually indicated there may be finite time blow-up, and there was a conjecture by Maida that there is finite time blow-up, but then it turned out that there is in fact global regularity, just very fast growth in curvature of the patch. And in situations with boundary, results have been limited. They mostly address the situation where patch starts away from the boundary, or it's only for local results, or with loss of regularity. So for modified SQG, it's a bit harder. I will have a slide where I'll just very, very naively explain why. But local regularity was shown by Rodrigo and Gancedo. Gancedo in Sobolev space, Rodrigo in smooth class. And on the other hand, there is numerical evidence by Cordoba, Fonteles, Mancio, and Rodrigo that there is a finite time creation of corners and patch touching. So the setting I will be interested in is half-plane. So it will be half-plane with no penetration boundary condition. And so the first result, and it's a joint work with Rizik, Yao, and Zlatosh, is that in the Euler case, there is global regularity in this setting. So if you start with C1 gamma patch, it's a regularity of the boundary, then there is unique C1 gamma patch solutions. Patches don't touch, don't self-intersect. So here, patches are allowed to touch the boundary. So now, next result is when alpha becomes greater than 0. And so if alpha is between 0 and 1 over 24, the following holds. If we start from H3 patch, then there exists a unique local H3 patch solution. And so let me say a few words about what enters here and maybe a little bit why 1 over 24. So if you have alpha which is positive, you can't expect your velocity to be a Lipschitz, right? It's log Lipschitz for Euler, and now it's only Hölder. And of course, that may give you problems when you work with trajectories. Uniqueness is not clear. And trajectories are very useful. So here's a very naive argument, and it's not really the whole story, but why things are not as bad as you may think. So it's actually normal velocity that matters for patch evolution. Tangential shouldn't do much to a patch. And if you look at the normal velocity, what you realize, so this is like a normal velocity at the point here, and if you integrate over this rectangle, something like this, and vorticity is, let's say, 1 on omega j, then you get 0 by symmetry. This is odd, so this integral will cancel. And so then what will enter into the normal velocity is just points from here, which are completely harmless, they're away from singularity, and these little discrepancies, which are not in the patch. So these are cusp regions, okay? And so they actually are thin, and because of that, your normal component is better than tangential, in fact. And in case of the boundaries, it's a little trickier, because a boundary with boundary, no penetration boundary condition is, by reflection principle, is equivalent to another patch sitting on the other side. You can just remove the boundary and put the patch there. But then you see that there are cusps, in fact, where patches touch the boundary. And so the estimates near these points are hard. Okay, so in particular, the tangential field of this reflected patch will strongly affect the original patch, and tangential field is not very nice. So, and here's the third theorem. So we have that, by 1 over 24, I doubt that it's sharp for this theorem, but going all the way to 1/2 looks quite hard. But some progress should be definitely possible. So the third theorem is in the same range between 0 and 24. There exists initial data such that the corresponding patch solution blows up in finite time. Okay, so in fact, you could say that this couple of theorems show that in this context, 2D Euler is really critical, right? In the context of patches on a half-plane, you have global regularity for 2D Euler. As soon as alpha becomes greater than 0, you get finite time blow-up. And the scenario for this finite time blow-up also has odd symmetry. It's a hyperbolic point on the boundary. And the idea of the proof is basically as follows. We take a barrier inside of a patch, and I'm looking only on 1/2 of the picture, and then by odd symmetry there is another part here. So initially this barrier is inside the patch, and we define how it moves, and in particular, so this front here is x, so it moves so that in finite time it gets to the origin. And then we prove that, in fact, barrier cannot cross the patch. It cannot cross the patch, and if patch stays regular, and that would imply then that the patches actually collide, and so in finite time, right? Because there is another patch approaching from the other side. And in this argument, kind of connecting to the Boussinesque situation, what you discover in this argument, so to show that the patch cannot break through, you have to look at a point of touch. You assume they actually touch. And then you estimate velocity at this point of touch. And there is a good part of velocity. Well, it depends on what you want. If you want to blow up, then there is a good part which pushes patch forward, and there is a bad part in Biot-Savart law which pushes in the opposite direction. And these two parts turn out to be of the same order. In fact, after some estimates, one can estimate that the good part is the integral of this Biot-Savart law over this region which is called good, and it's a bound from above. It's a negative bound. And the bad part comes from this region. So otherwise there are cancellations that you can control. And as you see, they are of the same order, but as alpha becomes small, this coefficient actually goes to infinity, while the coefficient in front of the bad part converges to a constant. And geometric way to see it is that when alpha is small, the G region is larger, and it's a longer range kernel, so G wins. While when alpha approaches 1/2, for example, singularity becomes non-integrable, and the bad region sees larger angle of that singularity, pi, as opposed to just pi over 4 for the good region. And so, at least in this case, even though they're the same order, there is a small parameter that you can play and get finite blow up in this setting. And yeah, I will stop here. Thank you.
Are there any questions or remarks?
Yes, regarding the SQG patch problem, so the local existence, you require that they self-intersect in two patches, right?
Yeah.
On a segment, right? Is that correct?
Uh-huh.
Is there any hope to do it on a single point and to prove local existence?
Oh, so...
For a very small alpha, is there...
I think it will work the same way.
It will work, oh. Okay.
Yeah, it should work the same way. Mm-hmm.
But
as far as the boundary has the right regularity, right?
Mm-hmm.
So we need H3. So if you have H3 patch, which touches just at one point the boundary, there is local theory.
and global and singularities?
Oh, that is not clear. I wouldn't bet on it. Because we really need barrier to have a foundation on the boundary, and you need barrier to have certain mass, right? So I'm not prepared to say, not obvious.
Thank you.
Any other question or comment?
So in the case of axisymmetric 3D Euler, you mentioned result of growth when time goes to infinity, but you didn't say, do you have the double exponential growth?
Sorry.
No, I mean, when you spoke of the axisymmetric Euler.
In 2D Euler?
No, in 3D axisymmetric Euler.
Yes.
I guess that at some point you mentioned a result of growth of the norms when t goes to infinity. Or maybe I didn't understand.
For the models, right? For 3D Euler, well, there are examples with growth. I didn't speak about examples with growth. Blow up so far has been proven for some models.
No, but I was speaking not of blow up, but of growth.
Growth.
And so you mentioned some result about growth, but you didn't say exactly how much it grows, I guess.
Let's see. So I don't think I mentioned growth, right? But there are definitely examples for 3D Euler with growth. I mean, one could just transport 2D examples to 3D. Yeah, but so blow up is open.
No, but actually, I was thinking to 3D Euler without swirl.
Yeah.
So in the case when there is global existence.
Oh, 3D Euler sorry?
Axisymmetric 3D Euler without
oh, you mean for the case with zero swirl?
Yeah.
Oh, for the case from zero. Yeah, I didn't talk about it, but there is actually an interesting work. Yeah, so there is a work about 3D Euler without swirl by Tam Do, where he shows that, well, the upper bound is double exponential, as you would expect, but at the axis, it's actually simple exponential. So at axis, it's different from the rest. Of course, axis is very interesting part of the region. But I don't think he builds an example with growth, actually. Yeah.
Any other question or comment? Okay, otherwise, let's thank Professor Kiselev again.